Hello, this is section 4.4, Systems of Equations in Three Variables. Part 1, Solutions to a System of Linear Equations with Three Variables. Definition 1. A solution to a system of three variables equation is an ordered triple ABC that is a solution to all equations. Example 2. Determine whether each ordered triple is a solution to the system. X minus y plus z equals 2, 2x minus y minus z equals negative 6, 2x plus 2y plus z equals negative 3. And the first point is negative 2, negative 1, 3. Let's plug that in. We get negative 2 minus negative 1 plus 3, and that does equal 2. So that checks out. And then we have 2 times negative 2 minus negative 1 minus 3. That does equal negative 6, so that checks out. And then we get 2 times negative 2 plus 2 times negative 1 plus 3, and that does equal negative 3, so that checks out. So since the point worked in all three equations, yes, this is a solution to the system of equations. The second point, negative 4, negative 3, 4. So does negative 4 minus negative 3 plus 4 equal 2? Well, no, it does not. It actually equals 3. So this point is not a solution to the system of equations. Geometrically, we can think of a solution to a system of linear equations as the place where the graphs of both equations intersect. Now that really should say all equations intersect. In 3D, there are three possible outcomes, but multiple ways these can occur, unlike with lines in 2D. So you can get no solution. You can get infinitely many solutions. Remember, when you get infinitely many solutions, your answers will look something like x comma y comma 2x plus 3y. So this is saying x and y can be whatever, but then your third coordinate is a linear combination of the first two. So that one has two free variables, or you can only have one free variable. Z plus 2, 1 half z, and then your third variable's free. Now I just randomly checked where the free variables are. Like for the first one, I said x and y. It could be x and z or y and z. Or for the second one, where there's only one free variable, it could be x, y, or z. It doesn't have to be z. And then you can only get one solution as well. And that's where you're going to get an ordered triple, like 1, 2, 3, or x equals 3, y equals negative 1, and z equals 11. That's what your answers will look like when there's one solution. Part 2, solving systems of linear equations with three variables. We already have techniques to solve systems of two linear equations with two variables, so we'll work to rework our system of three equations to use existing techniques. Example 3. Solve the system of equations x minus 2y plus z equals 3, 2x plus y plus z equals 4, 3x plus 4y plus 3z equals 1. You pick two pairs of equations to start with. Eliminate one variable by using the properties of equality in each pair. The eliminated variable can be either x, y, or z, depending on what looks simpler to eliminate. But you must be eliminating the same variable in both pairs. That's the important part. That is the same variable in both pairs. So now usually when I do this, I do label my equation. So I'm going to call the first equation A, the second equation B, and the third equation C. And when I look at the variables, the one that looks easiest to eliminate to me are the z's. So I'm going to take A minus B. So that'd be x minus 2y plus z equals 3. And 2x plus y plus z equals 4. So x minus 2x is negative x. Negative 2y minus y is negative 3y. Z minus z cancels out. 3 minus 4 is negative 1. And now I need another set of two pairs, so either A and C or B and C. So I'm going to use A and C. It doesn't really matter. But I have to eliminate the z's because it has to be the same variable as the first pair. Well, that means I have to multiply a by negative 3. So I'm going to go negative 3a, which is negative 3x plus 6y minus 3z equals negative 9. And then I'm just going to take c. So 3x plus 4y plus 3z equals 1. And actually, the x's and z's cancel out here. And we're left with 10y equals negative 8. Step 2. The above elimination steps will result in two linear equations and two variables, which we know how to solve. Solve the equation using substitution or elimination. So normally, the two equations you get in step 1, oh, I forgot to label them. Let's call this one B and this one E. So usually D and E both have two variables. In this specific example, E only had one variable. So I am going to just take E and solve for Y. So then I get Y equals negative 4/5. Okay. But otherwise, you can use the methods from the previous sections that we talked about of elimination or substitution at this step. Step 3, resubstitute your solution from step 2 into any original equation. Again, this makes a linear equation with only one variable. So to solve this equation for the only variable it has. So step 3 is to take your answer from step 2 and plug it into one of the equations from step 1. So either D or E. Well, if I plug it into E, I'm not going to get X. So I'm going to plug it into D. So then we get negative x minus 3 times negative 4/5 equals negative 1. That's negative x plus 12/5 equals negative 1 minus 12/5 minus 12/5. We get negative x equals negative 17/5. And divide by negative 1, divide by negative 1. And we get x equals 17/5. So now that I took step 2 and plugged it into step 1, you now take step 2 and step 3 and plug it into A, B, or C. So you plug it into one of the original equations. So then, let me scroll back up real quick. Let's plug it into the first one. X minus 2y plus z. So x is 17/5 plus 2y. Sorry, minus 2y plus z is equal to 3. And now I go ahead and solve for z. So we get 17/5 plus 8/5 plus z equals 3. 17/5 plus 8/5 is 25/5, which is 5. Subtract 5, and we get z is equal to negative 2. And step 4 is just to write your final solution, which is 17/5, negative 4/5, and negative 2. That's it for this first video.